So let's look at an example where we use the technique of interchanging the order of variables. We're going to apply Fubini's theorem. I don't know if it's actually technique number 1. I think I listed it as technique number 2 on the list of learning goals. That's okay. It doesn't matter. So let's say that we have a rectangular region that goes from -1 to 2 in the x direction and from 0 to 2 pi in the y direction. And let's say that our function in this case is given by f of xy is equal to 3x squared times the sine of y. So to set up this double integral, I'm going to start by having my x values be on the interior. So let's say that my x goes from -1 to 2 of this function, x cubed sine of y dx, because my differential has to match the bounds. And then my outer integral is going to be where y goes from 0 to 2 pi, and my outer differential has to match the outer bounds. So in order to compute this integral, I'm going to start by taking the integral of the interior function. I'm taking an integral with respect to x, so I treat the sine of y as a constant. And when I integrate this, I see that I get x raised to the 4th power times 1/4. That's polynomial rule for integration, multiplying by the reciprocal of 4. And then the sine of y is just a constant, so I just bring it along, sine of y. And I'm going to evaluate this whole thing as x goes from -1 to 2. And don't forget that we need to have our exterior integral, because we haven't evaluated that. Maybe this is getting a little messy. Y equals 0 to 2 pi. So let's go ahead and evaluate this. So when my x value is equal to 2, I plug 2 in for x, and I get 2 to the 4th, which is 2, 4, 8, 16. I totally know that. Divided by 4. 16 divided by 4 is just 4. So I end up with 4 times the sine of y. And then I subtract, plugging in -1 for x. -1 to the 4th is going to be +1. So I end up with just subtracting positive 1/4 sine of y. And then I need to take the integral of this as y goes from 0 to 2 pi dy. Again, I'm going to rewrite it up here just for clarity's sake. So 4 minus 1/4 is going to be 15/4 times the sine of y dy. Evaluating this as y goes from 0 to 2 pi. So now I need to integrate the sine of y with respect to y. And when I integrate the sine of y, I end up with negative cosine. So 15/4 is the coefficient. 15/4 times negative cosine of y. And for my cosine values, I see that my y is going from 0 to 2 pi. So I need to evaluate the cosine of y at 2 pi, which we know is just equal to 1. So I get negative 15/4 times 1. And then I subtract negative 15/4 times the cosine of 0, and the cosine of 0 is also 1. So I'm subtracting negative 15/4. Subtracting a negative means that this is a positive, and I end up with the fact that this whole big integral thing was equal to 0. That in and of itself maybe isn't that surprising. I have this periodic function. So far we haven't seen functions that dip below the xy plane, but that would be interpreted as negative volume, just like when we dip below the x-axis, that's interpreted as negative area when we do integration. So this is done this way, and we notice these were the steps that we went through. Now, let's interchange the order of integration and see what we come up with a second time. So when interchanging the order of integration, instead of having the x on the interior, I'm going to now flip it around. Let's make this dy dx. We know we can do this y because of Fubini's theorem. So my dy is in the interior, so I need to make sure that I have my bounds of y on the interior. So y is going from 0 to 2 pi. The x is on the exterior, and my x values in this case are going from -1 to 2. So now when I integrate, I'm going to integrate with respect to y first, and I'm thinking of my x cubed as a constant. So when I integrate with respect to y, I'm going to get x cubed just as a constant along for the ride, The integral of sine is negative cosine, so this becomes negative cosine of y. I'm going to evaluate this as y goes from 0 to 2 pi. And of course, I need to take along my exterior x integral that we'll get to in a second. So let's evaluate this interior as y goes from 0 to 2 pi. Again, we see that the cosine of 2 pi is 1, so I end up with negative x cubed minus the cosine of 0 is also 1, so I end up with negative x cubed again. And I get negative x cubed plus x cubed, not forgetting, just for notational sake, my exterior integral. The interior of this simplifies to just 0. Negative x cubed plus x cubed gives me 0. So now I just have the integral as x goes from negative 1 to 2 of 0 dx. And this was cool. So the first way that we did it, we had to do all of the steps of all of the integration for the x. But now we see that, at this point, we've already gotten zeros, and we see that this is just 0 and this is just 0. The integral with respect to x of this 0 function is going to be 0. So the cool thing about this is that we've just evaluated this much faster and simpler because we interchanged the order of integration so that we did the y's first instead of the x's first, and it meant that we got to eliminate a bunch of the steps in our process. This is something that's going to become even more important as we see examples in 15.2 in which we need to interchange the order of variables just to be able to integrate the function. So my final example for today is the technique of separation of variables. So for this example, I'm going to highlight the fact that for functions that are products of single variable functions, we're able to split these apart into two separate integrals. And I'll show you what I mean in a second. So let's say that we're integrating over the region where x's go from 0 to 3 and y's go from negative 1 to 1. And let's say that our function is given by x squared times y. So when I set up this integral, again, it doesn't matter which integral values we start with, but let's say that the exterior, my y values are going from negative 1 to 1. For the interior integral, my x values are going from 0 to 3 of this function x squared y dx dy. And just like we saw when we just took the integral where we had our x to the cubed and sine of y functions, we saw that for this first integral, the inner integral, I'm treating y as a constant. And so really I'm just integrating with respect to x. And when you integrate with respect to x and treat y as a constant, just like we had as our integral rules from previous calculus courses, things that are constants, we're allowed to pull outside of the integrals. And that same technique holds here, that I could, just like how we saw, the y just sort of went along for the ride. It didn't actually impact the integration with respect to x. I can pull the y out of this integral, and it means that this is the same thing as the integral as y equals negative 1 to 1 of y times the integral as x equals 0 to 3 of x squared dx dy. And notice, this is where it gets a little more abstract. Now this interior chunk here, I only have x's, right? I'm integrating with respect to x, but all of my variables in this chunk are all x's. And x's we treat as constants when we integrate with respect to y. So if I were thinking of doing this outer integral, it doesn't really matter what number comes out of this messy stuff. Whatever it is something that's just going to be a variable with respect to x, which doesn't matter for this integration. Namely, that this whole thing can be thought of as a constant when we're integrating with respect to y. So if I wanted to, I could take this whole constant and pull it outside of this function, meaning that I could rewrite this by pulling this outside of the function. I'm saying that this whole chunk could be thought of as a coefficient on front of the integration with respect to y. So here's this chunk, my x's, which I'm thinking of as constants because I'm integrating with respect to y, times the integral of y dy, as my y's go from -1 to 1. So all of this talking is just saying that if I have a function that can be separated into a function of x and into a function of y, I can think of the product of those two functions as the product of the integrals. Let me say that one more time to make it clear. I think that it's clear in my head, but I want to make sure that it's clear for you. So in this case, I can think of this x squared times y to be equal to some g of x function that's just a function of x's multiplied by some h of x function that's just a, h of y function that's just a function of y's. So when I end up taking the integral of this, I can separate the integral into the integral just with respect to the x's and just with respect to the y's. So finishing the solution of this problem, if I just take this integral with respect to x, it's exactly the rules that we know before. I'm going to use polynomial rule again, and I get x cubed times 1/3 evaluated as x goes from 0 to 3. 3 cubed is 27 divided by 3 is going to be equal to 9, times this integral over here. I integrate y with respect to y, and I end up with 1/2 y squared, which is evaluated from y equals -1 to 1. I plug 1 in and I get 1/2. And then I subtract. When I plug -1 in, I also get 1/2. Oh, maybe I shouldn't have picked symmetric bounds because it's sort of boring. And I end up with 9 times 0, which is 0. But the moral of the story is, and this is what we'll generalize, the moral of the story is the fact that, I'll write this down and we can apply it later. If f of xy, a two-variable function, can be written as a function of x times a function of y, then I can break apart the double integral. The double integral of f of xy dx dy is going to be equal to the single integral of g of x dx multiplied by a single integral of h of y dy. And sometimes this will save you some work, just saves you some penmanship. And sometimes maybe it would even help with your integration, that your integration looks cleaner and less sloppy. So that's all I have to say about section 5.1. Today we talked about two different geometric interpretations of Riemann integration. One where we had all of the Riemann sums of those rectangular solids that we added up to get the volume of the entire solid. We also talked about our slice of bread analogy to be able to lead to Fubini's theorem, where if you slice the bread this way or if you slice the bread this way, adding up those volumes, you'll get the same number either way, which allowed us to interchange our order of integration. It didn't matter whether we did the x's first or the y's first. And then finally, we talked about this technique of separation of variables, where if we have a special function that can be separated into a g of x function and an h of y function, it means that with integration, I can pull the integration apart and think of them as integration of single variable problems.